to our keynotes. It is a pleasure to introduce today's keynote speakers, a father-daughter team. What a duo, whose combined work has been at the cutting edge of climate science for the past 50 years and is a living example of the importance of passing knowledge from one generation to the next. Dr. Richard Alley of Pennsylvania State University is a Nobel Prize winning climate scientist who is one of the most influential glaciologists of our time. His pioneering ice core research has helped to reveal how quickly climate can change, and he has spent his lifetime bringing clear, engaging science to educators, policymakers, and the public. Dr. Alley was also a keynote speaker at yesterday's Project 2100 conference, and some of your students attended. Joining him today is his daughter, Dr. Karen Alley, from the University of Manitoba. Karen's research focuses on glacier and ice sheet dynamics, including how ice interacts with the ocean and what that means for future sea level rise. Her work represents the next generation of discovery using new tools and perspectives to answer urgent questions about our changing planet. I should also introduce, and I was voluntold to do this by someone very special in the audience, 3 VIPs related to Karen and Richard who are in the audience. Richard's wife, Cindy, who is also a geologist, and their other daughter, Janet, who, like many of you, is a science teacher from Seattle. Trying to make a difference each and every day. Here's the VIP. Richard's granddaughter and Karen's niece, Samantha, is also with us. And by the way, and Samantha told me I have to say that she just turned 7 last week, so happy belated birthday. And she loves dinosaurs, like my 6-year-old does, and is excited to visit the Field Museum tomorrow. So that's going to be exciting. And it's a tour of the city before you fly back out. Together, Karen and Richard offer something special to shared multi-generational commitment to science and the future of our planet. That's our goal after all, multi-generational. Their partnership reminds us that mentoring and inspiring the next generation of climate scientists and policymakers is what will ultimately shape the fate of our planet. So, join me in welcoming Dr. Karen Alley and her dad, Dr. Richard Alley.
Well, thank you so much. Am I on here? There we go. Thank you so much. It's truly a pleasure to be here today. We have many people to thank in being here. So, a few names on there. Jeff and Brian, all of the people here who have volunteered their time to put this together. Bill Grosser and Louise Huffman, those are the two who kind of dragged us into this whole thing to begin with. Lots of people really contributed to this. It is a privilege to be here. Our science doesn't matter until we communicate it, and you all do something useful with it. So we hope we can do some of that for today, and thank you for being here. There'll be a few penguin pictures throughout. All right, so what we're going to do today is we're going to tell you some things that you already know, I'm sure. STEM opens doors. We're going to talk about some of the doors that we get to through our field. It works. We have solutions at our fingertips that we can use to solve climate change, which is going to solve a whole bunch more problems in our world at the same time. We do have hope in all of this. This is my family. We've introduced them already. This is not a recent picture from Alberta on Athabasca Glacier. So there's my sister, there's my mom. You can flip to the next one there. So my sister, as was said here, is a science teacher in Seattle. My mom has a geology background. Now she is a brilliant quilter. And me and my dad there, I swore all my life I would not be a glaciologist, but this is the most enthusiastic scientist I've ever met. It's hard not to get excited about this. Janet even spent some time as a ranger at Mount St. Helens. She said this from kindergarten, that she was gonna work with volcanoes, so that's her out at Mount St. Helens. In my other life, so I'm a glaciologist. I study ice-ocean interaction. I'm also a musician. This is me, the only time I've gotten to play my hammered dulcimer on a glacier, which was unbelievably cool. You can find it on YouTube if you want to find it on YouTube. So I do work on mostly Antarctica and the Canadian Arctic. I've had the privilege to go down and work on Thwaites Glacier. Some of you were at our sessions earlier. We have some virtual field lab opportunities to learn about what Thwaites Glacier is doing now, what it will do in the future. I've worked with just some phenomenal people out in the field trying to get the measurements we need to understand the change. I'm also working in the Canadian Arctic. I have, if you flip to the next one there, I have a field program with some great students, great colleagues up on Baffin Island. If you ever get a chance to get up to Baffin Island, get up to Baffin Island. This is Auyuattuq National Park, where we do a lot of work on ice-ocean interaction. This is Coronation Glacier, that's a tidewater glacier there. We fly drones, we do ocean measurements. We're trying to get at those processes that are controlling our future in sea level. Now, I have the privilege to work with some great students on this project. Our field, what we do is the research, right? That's what my dad and I have decided to dedicate our lives to. Yeah, you can flip to the next one. So we get to go into some of the most beautiful places on Earth, which is a deep, deep privilege of our work. We get to work with fascinating people, learn new things. That's what research is all about, is coming up with new things that nobody knew before. And then we get to share that knowledge with others. It also means that we create a space for people to learn how to be creative, to go off in directions that matter in the real world. A lot of our students end up doing glaciology. A lot of them end up doing lots of other useful things with their STEM background. I haven't been in this that long. I don't have many graduating students. Kelsey Voss, though, was one of my master's students. She worked on Greenland tidewater glaciers. She's now spending her life doing environmental artwork. So we get a lot of different directions from STEM fields.
Right, so we'll switch that. In case you were curious, she had to put little reminders to me as to who's speaking next. So that code is who's speaking next. But at any rate, I'm an old guy. I've been at this now for almost 50 years. And, you know, I've got a background in geology and some engineering in that, why things break and why things don't break. And I get to work. I've done a little on erosion and a little on climate history and a little on collapsing ice sheets and a lot on meeting other people and doing exciting things. These are current grad students or very recent ones. And at the moment, Emma is up on Svalbard. Thomas is actually in Iceland. The glacier is melting on Iceland. That takes the weight off of the volcanoes and they erupt more. And his job is to predict the volcanic eruptions for the people. And we were Zooming with him not that long ago, and he said, if I lean, I can see the volcano. A few of the other students and where they're going. Some of you got to meet Luke Zoot. He is here doing brilliant things. He's a professor in Wisconsin, and Knut is a friend, and he's a professor in Washington. But Rebecca did Antarctic glaciology, and then she's off doing big data for new energy sources. And I'm going to tell you just a couple other stories. Just a couple, right? Greg Jablonowski went to Greenland with us a few years ago. He was an Air Force ROTC guy. He worked on these ice cores, and he was doing sound velocity in the ice, mostly for C-axis fabrics, but if there's a crack, it slows down the sound. And he graduated, and he's Air Force, it's ROTC, so they put him in charge of making sure that the planes are safe, the fighter jets. You've got wings. They have a structure. You can't see that structure because it's under the radar diffusing skin, but you can use sound to see if there's a crack in it. And so he had been learning what's needed to keep the fighter jets safe by doing ice cores in Greenland. Right? And Lizzie, this is her setting a little seismic charge to make noise to find out how thick the ice is and things about it. And after she did Antarctic work and some work in the Swiss Alps, she went off to build water systems for people in the South Pacific, and then she came back to make sure that the hillsides weren't going to fall off while they rebuilt LA after the fires. So some of the things, some of us go straight through. You get a PhD in this, you do this. Some of us take this and you do very different things, but it's always the same. The STEM opens doors. And so let's stick with that, and we'll go back to Karen.
STEM is problem solving. right? Like that's what we're trained to do. We solve problems about glaciers. We're not going to talk that much about that today. What we're going to talk about is the other problems that we can solve that have a lot to do with responding to the changes that we see in glaciers. Science works. I hope I don't have to convince you all of that. You're in this room already. Science works. I don't have my cell phone in my pocket, but there you go. Most of you, I'm guessing, have a cell phone in your pocket. So if we were to take some sand, some oil, a little organic material, some rocks, you could build a cell phone, right? Those are the ingredients for a cell phone, right? A little sand, silica makes the glass, get the right rocks, we get the right components on the inside, a little bit of organic material to make the plastics on the outside, it's a cell phone. Well, there's a whole lot of science behind that, right? This is proof every day that science works. And furthermore, you use that phone now for a lot more than communicating with people. We found our way here today by turning on the GPS directions that said, "Are you ready to go?" and gave us left and right turns. Turns out that it's about 2 minutes of driving before your phone would be completely lost if we didn't have quantum physics in that computing power. Science is in everything that we do every day. And that means that we've solved problems and we can solve the biggest problems that are facing us. We're going to focus on energy today. Right now, we have lots of energy available to us. There's lots of energy powering this room, that's powering this microphone, that's powering this projector and these lights. We have lots of value in that energy, but we also have problems facing us in this. There is a lot of danger in continuing to use energy the way that we've been using energy. But what that also means is that there are huge opportunities as part of this. When we think about energy, where we get our energy, just to put it in perspective, right? All of us are good at creating our own energy to fuel our own bodies by converting food, right? We eat food every day, that's converted to energy. If we say we take about 2,000 calories in per day, give or take, that would power about a light bulb for a day. Biological energy is super inefficient for this. We think about, okay, I could power a light bulb with the energy that I take in, but boy, I'm using a lot more light bulbs and a lot more sound equipment and a lot more heating and cooling. And when we think about what's done in the US for everybody in this room, you're using about 100 times that amount of energy every day. That's what you rely on. The world average means we have some differences in terms of what energy is used. World average is about 25 times what you produce yourself per day. Poorer countries don't have that availability. They're using about 4 times what people create themselves today. There's many, many components to this. There's inequalities in this. Most of that energy that we have right now comes from fossil fuels. About 80% of world energy right now relies on fossil fuels. You need to be a little bit careful with that number when you think about what kind of energy we're getting from that. Our lighting is getting more efficient over time, but you remember older light bulbs for sure. If you touch those light bulbs, they burn your fingers, right? And we're still losing a lot of that energy to heat. A lot of it's escaping as we try to use that energy. So not only are we using this source, it's not particularly efficient to begin with.
All right, so we have to change, right? And I've got a couple of things up here. First commercial oil well, 1859, is drilled where oil is leaking out of the ground. The native people had used this oil for thousands of years for waterproofing and in other ways. Oil was easy. And as I might have mentioned, I'm old. There are a few of you in this room who are old enough to remember when there was a situation comedy on television about our energy system. I see a nod or two, right? It was called the Beverly Hillbillies. And it was a story about a man named Jed who was a poor mountaineer and he barely kept his family fed. And one day he was shooting at some food and up through the ground come a boiling crude. Oil, that is, black gold, Texas tea. The idea that you could find oil in your backyard was still plausible when I was a kid. It is complete nonsense now. Right? Just absolute, undivided, complete nonsense. Why are we fracking the county? It costs $1 billion plus to build some of these oil platforms in deep water because the good oil, the easy oil, is long gone. There's a very important metric that we sometimes deal with. I'm not sure what happened when I powered up people. I ran out of energy. So. We're good. Bad battery. Okay. So there's one of the key metrics is the energy return on energy invested. When they had to go get oil from an oil seep in Pennsylvania, you had to pick it up. That takes a little energy. Easy oil was really big return, little investment. Probably now the renewables are a lot better than new oil. Okay, that's important. But be clear, there's a lot of really bad oil out there. Coal that you have to take off the mountaintop, and oil shales and tar sands and so on. We can burn a lot more if we don't get ourselves together. But there's no possibility of talking about sustainability. We're burning oil and coal and gas 1 million times faster than nature saved them. It's 100 million years to get more of them. And what's really important here is that there's no way that the rest of the world can think about getting what we have with a scarce resource. And if the world wants to be energy rich, if we want to give good things to everyone, we got to do something else, okay? And then we get to this piece, which is if we burn before we learn, A, we're in deep doo-doo because we don't have the energy, and B, we've changed the climate in ways that make life really, really hard. So this basics, right, 1824, Fourier figures out there's a greenhouse effect, Fourier series. Eunice Foote in the US, she did these brilliant experiments in the 1850s. Then Tyndall, its CO2 is a big chunk of the greenhouse. By 1896, Arrhenius has said burning fossil fuel will warm the world about this much. Arrhenius didn't yet understand quantum mechanics, so his calculations weren't quite as good as modern. Our modern understanding grows out of work that the Air Force did out of World War II. They're worried about things like protecting our big cities from enemy bombers. If you could see the hot exhaust of the enemy bomber, you can have your heat-seeking missile fly up their tailpipe and make sure they don't blow up your big city. If you put the wrong sensor on, you can't see anything because CO2 absorbs the infrared. And so they are able to predict what satellites will see when they go up and look down, and how that will change as we change the atmosphere. They were right, okay? In some very real sense, saying that we don't understand global warming is like saying the Air Force doesn't understand how to target a heat-seeking missile. It's total nonsense. This is the Earth sending back to space the energy we get from the sun, and this divot is CO2. And they predicted that, and they predicted how it would change as you add more CO2. Okay, there is no other side. There's no other way to interpret this. This is an interesting plot. The red curve, starting in 1900, is the temperature of the Earth. All the black and gray curves are what was told to oil companies by their own scientists was going to happen. And each one of these lines starts at a time and it goes up. And if you average those, they're just about spot on. Right now, there's a whole lot of public scientists that said the same thing. These just happen to be the ones that were working for oil companies. There's nothing new here, okay? So like it says there, the warming effect of CO2 is not the least bit surprising. We've known it for a very long time. But when Arrhenius did this in 1896, he said, I don't think it'll ever matter. He said, I don't think we'll ever burn that much. His science was pretty good, his economics stunk. Okay? And I've got a scaling here, averaged over sort of my lifetime, that what we throw away at the curb for the trash collector is 0.5 ton per person per year. That's sort of a disturbing number. What our share of the CO2 is sort of 15 tons. Right? All those coal trains are full of stuff, and when you burn it, it's still stuff. And all those oil tankers are full of stuff, and when you burn it, it's still stuff. And yes, that cannot do anything except change the climate. It has to, okay? So we will come back in a little bit to good news. I'm going to do the tiniest little bit of really, really bad news first, and then we'll get to the good news. So there's a few sort of big picture things. If we burned all the tar sands and the oil shales and so on, we can cause much bigger changes in the future than we've had in the past. We had adaptive capacity when I was little. We're using it up. And as we use up that adaptive capacity, as we move out of the band where we can deal with it, the costs go up a lot faster than the temperature. I've got a bunch of slides of, now it floods streets in Miami on high tides. But they just wait for it to go down. And then sometime in our students' lifetime, that water gets into the water system, and it's salty, and they have to spend billions of dollars to fix it. So the costs go up faster than the temperature. It's a super linear system. We had some people that liked it warmer, but as we move outside the adaptive capacity, nobody does. It's getting bad for everybody. And very clearly, the uncertainties are on the bad side. We're still working on thwaites. It still could collapse. You look at this and say there's an uncertainty in sea level. It could be a little lower. It could be a little higher. The ice sheet could do something bad, and it could be way higher. And there isn't a real good side to offset that bad side. And what do we worry about? Right now, people are dying of heat. But there's nowhere on Earth that is so hot that you have to die if you're not protected. Our students, you young people here, could live to see a time when there are places on Earth that are fatal for an unprotected human. You are sitting there in the shade, in the wind, drinking water, naked, and you're going to die because your body can't lose heat to the environment, and you're making heat inside from your food. Okay? Way before that, your crops are in trouble, your farm animals are in trouble, and nobody wants to be the person who proves that it's fatal. So now your country and your borders are in trouble. Okay? Sea level rise virtually guaranteed. Warmer air has more water when it's ready to rain, and so it gives more intense rainfall, and we're seeing more floods coming from that. Every clothes dryer in the world has a heating element because it dries it out faster, so you go to more droughts. There's more energy for the strongest storms. You lose a line of defense against certain diseases. We're trying desperately to save rare and endangered species, and they're in trouble. And as we'll see in a little bit, this is especially bad for poor people in hot places who aren't actually doing it. And so we've got the slides. We can show you all this stuff. It's not good news. But
have we depressed you suitably yet? There is good news. There's a lot of good news left in this. When we think about that idea of business as usual, whatever that means, right now that still means burning a lot of fossil fuels. We compare what we could do. We have a lot of opportunity in this. We could end up with a larger, stronger economy, more jobs, improved health, greater national security, a cleaner environment, and a more moral society that takes care of each other. So we're going to take a slide for each one of these.
Right, so we'll tag team. I'll start this one. I served on a committee with Bill Nordhaus. He won the Nobel Prize in Economics in 2018. And brilliant, wonderful person. And he built tools to help policymakers make decisions. You're in charge. You're in charge, and you're in charge. You folks are in charge, right? You're the students here. We were having a chat earlier. You have resources. People want them. They want food. They want housing. They want education now. But they want to invest in infrastructure and roads and more education and other things for the future. And they want to target that investment for particular things like curing malaria or solving climate change. So Consumption today, broad investment, targeted investment. How do you decide where to put your money now? And what he did was build the tools that allow you to look what gives the most good to the most people. When you run those tools, they invariably say now that we are under-investing in climate change. That the economy is better off, more people get more good if we invest more in heading off climate change. You will meet the person that says, oh yeah, climate change is real, but we can't afford to deal with it. The Nobel Prize in Economics says we can't afford not to. Okay? Better economy, there's number one. Number two, jobs. I worked for an oil company one summer. A few of our students worked for the oil companies. My dear wife worked for the oil company one summer. They make a lot of good jobs. It is fairly clear that anything else that we do for our energy system makes more good jobs. More good jobs by getting off fossil fuels. And a lot of that comes up to something that the economists call rent. Modern oil production is hard, it's expensive, it requires high fossil fuel costs. But the oldest oil, which might be coming from Russia or somewhere else, is still really cheap to get out of the ground. They can find it, pump it, get it to the refinery for maybe $5 a barrel. But we're paying them $75. And the difference between that 5 and 75 is what an economist calls rent. And it doesn't have to hire anyone. It's profits that are not earned by paying workers to do good things. When you move off of paying that money for your oil, and you put it into conservation, you put it into renewables, anything else you put it into, you're hiring your students to do good things, rather than paying them because they control something scarce. And so pretty much anything else gets you more good jobs. Okay.
Number three is thinking about the health side of things, right? We heard a little bit about this morning in terms of heat waves, but actually the study was showing in 2021, gave some actual numbers this morning on what happened in individual heat waves, but if you put this in perspective globally, in 2021, that study showed 1 in 5 deaths globally, 20% of deaths globally was earlier than it should have been because of particles from fossil fuel burning, right? This doesn't include the heat. This is not part of that. 1 in 5 deaths globally was earlier than it should have been because of fossil fuel burning, because of putting particles in the atmosphere. We get off fossil fuels, we pretty much automatically extend life expectancies on Earth. What are we on, number 4? National security. So this is David Titley, a friend of my parents, who's living at Penn State, retired rear admiral of the U.S. He's Navy, right? Yep. Yeah, the U.S. Navy. I don't know my military ranks very well. Don't tell him I said that. So he's done a lot of work on this, and it's interesting to hear that the Navy, the U.S. military, actually pays quite close attention to climate change and what's going on because of national security, right? The changes that we're seeing in the Navy, it's maybe more concrete. We're talking about flooding ports, for example, dealing with having to have a fleet that's able to be mobilized, that's not being battered by storms, right? This is a matter of national security. We have to understand what's happening. If we get that under control, they've got an easier job. I think this is our last one on this, there's 2 more. The environmental side of this, of course, we know that we're seeing all sorts of ecological changes as we warm the world. The extinction numbers on this are scary. You might have heard that we're in a mass extinction, right? This is the human-caused mass extinction event. And what we mean by mass extinction is that in the mid-range scenarios, this is what we're in. By 2050, this is 24 years from now, we'll see somewhere between 15 and 37% of all species on Earth disappear. right? Just a few years from now, we're going to see a significant percentage of species on Earth disappear. We address this, we save our biodiversity. And we learn how to better take care of each other. Pope Francis had this great quote: "It seems clear to me also that climate change is a problem which can no longer be left to a future generation because of the graphs that you see here." So what we've got on the top here, this is CO2 emissions per capita, right? So at the beginning we were talking about we in the US use 100 times more than we can burn ourselves per day. Other parts of the world are using more like 4 times that number. They don't have access to the energy. When you look at those places on Earth in the red there, these are our high emissions areas. You look at the areas in the blue, well, a lot of those are close to sea level. A lot of those are the places that don't have the ability to adapt, and yet these are the areas that are considered most vulnerable to climate change. So close to sea level, areas that are hot to begin with, areas that don't have the resources to address this in a way that keeps everybody happy and healthy. So there's a huge imbalance here that we need to correct. So we've had all of those, right? There's possibilities in this. We started with, all right, we're on fossil fuels. This is a problem. There are possibilities if we can do something about this. Now we're talking. We're not just going to solve things like sea level rise. We're going to solve a whole bunch of other problems on Earth if we can figure out what to do about it.
So we're going to try to figure out what to do with it. We're going to show a little bit of the solution space. You saw some of this from Eric this morning. You'll see pretty much everyone in this space pointing at a lot of the same things now. This is not the whole solution space, but it's enough to show you that the solutions will work. And that's the key thing. So 2,000 calories per person per day, where do we get it? Everything in orange is crops. We plow it, we grow things on it. Everything in green, or this bilious yellow, whatever it is grazing land. We let the animals eat grass and we eat them or milk them or steal their eggs. This much of, just think about driving outside of Chicagoland in any direction and how many cornfields and soybean fields you see. We have changed everything in color on this map for 2,000 calories. Suppose that we decided to get rid of every bit of oil, coal, gas, everything else except solar with existing technology, and then we're going to build a bunch extra so the rest of the world can have a lot of energy. Just for demonstration, I'm going to put it in the Sahara. Now be honest, it's not all going in the Sahara. Some of it's on our roof at home. But if we decided to run the entire world on solar energy, that's it. Okay? Everything in color we've changed to feed us, that would power the world forever. Okay? Now be very clear, that's 30 years of building. That's a lot bigger than our roof at home. But is the resource there? Of course. Absolutely, unequivocally, it is there.
This was fun. So we learned a lot from this experience. So this is Earth the Operator's Manual. This was a book and a show that my dad was the presenter on. I was in undergrad at the time and got a grant so I could go be a film assistant. I was thinking about going into science documentary. So we learned a lot about this experience. We learned a lot about unusual ways to communicate climate change. He's known for slightly insane ideas about this, and he got us going bungee jumping. For this was bungee jumping off the climate roller coaster. So there's one shot of me bungee jumping in this, and just for the record, I had way better form than he did on the bungee jump. Watch the show. There's some interesting stuff in that. But one of the things that we learned about this from this show, the producers found some ranchers in Texas who had been really struggling. They were worried about their ranching going under at the time, and then they built windmills, right? So we talked about solar. Wind is this other huge opportunity for energy. And this particular rancher, as with many in the area that we got to talk to in this documentary, saved their ranch on wind energy. About 5% of their ranch land was turned over to creating windmills, to have that available, and it now provides more money than the entire rest of the ranch. They call this mailbox money. They just go out to the mailbox and there's money for them in the mailbox, right? Because their land is passively creating this. If we were to put wind farms on just the windy parts of the world, out in the plains, places like Texas, we'd be supplying 5 times more energy than the entire global needs. One of the International Energy Agency said this in 2020, is that when we're thinking about solar, when we're thinking about wind, but solar as well, this is the cheapest electricity in history, right? There's a lot of arguments against this. This is too expensive, it will take too much land. Boy, it sure doesn't for the ranchers, right? This is a small part of our land that we can turn into something that has huge consequences. And it has some side benefits too. Sometimes shade is important. This is a great image of the sheep hiding under the shadow of the windmill. Shade is in short supply in some of these areas. This is actually one argument you get against solar. You know, well, fine, we need that cropland. We need to be able to grow crops. Shade's going to be a problem for that. Probably not.
Right, so here's another version where shade helped. So this is an experiment was done in Germany. They built the solar high enough to drive a tractor under, and they planted various crops. Some of them to see what happens under the shade, partial shade, some of them outside. Now this blocks some sunshine for the crop, but it also blocked some evaporation of water. This summer, there was a drought. They grew more food where they were getting money from solar energy than they did where they didn't. More food because it managed the evaporation. So more food because you're also making money selling electricity, right? Agrovoltaics, this is really amazing. This paper is a few years old now. You could probably update it a little bit, but be very clear. We grow food and we eat it. We grow food and we feed it to animals and we eat them or milk them or steal their eggs. And we grow food and we burn it. And there is corn being grown around here that's in our gas tanks. There is sugar cane being grown in Brazil that's in their gas tanks. There is soy diesel. We have biofuels. We use something like 4% of our cropland for food to burn in a hungry world. And this quote from this paper, 1% of cropland would satisfy human energy demand. The land we use to grow food that we burn would power everyone forever. Now again, don't think that that's what you would do. You're going to put some of it on your roof. You're going to put some of the solar over the irrigation canal so that it slows down evaporation and you can grow more food. You're going to put some of it along the side of the road. But if you meet the person who says, oh, we don't have the land for this, if they're not screaming bloody murder about this, they've been confused about something. And this plot is basically, I think, what you saw this morning, but this is cost, 2014 up to very recent. Orange here, sun and wind, cheapest. Fossil is in blue, and offshore wind and batteries have basically caught up with fossil at this point. And remember that all these others are going down and fossil is not. And so at this point, far and away the cheapest stuff you can get, and the truth is you can take all of these cheap ones together and make something that supplies everyone forever and is cheaper than that. But there's an asterisk here. There's a tiny little bit of subsidy for these, and there's a huge subsidy for this one. So this is something that was done by folks in the International Monetary Fund. Direct subsidies for fossil fuels are huge, and they're bigger than for renewables. But the indirect subsidy, they can make you sick, they can change your climate, and we're not paying for it. This estimate from the International Monetary Fund, updated to last year, is that the subsidy for fossil fuels is bigger than the price of fossil fuels. It is 7% of the world economy, or more than $7 trillion a year. Okay, that's a big number. And if you were to go back to this one and take this blue and double it, it's nowhere close to being competitive. It's just not there, okay? Now, people are seeing this. They're making decisions on this at this point. So there's this interesting page that the World Bank maintains. How much of the money that is shipped overseas to buy things goes for fuel. And for the world, it's 13%, but for poor companies and countries, it's 28%. They picked one example, Nigeria, where it's 38%. This is money that you're buying fuel rather than medicine or food or books or computers or something like that. You're shipping that kind of money overseas just to get fuel. And so then there was this little calculation here, which is interesting. In Nigeria, solar savings from replacing diesel could repay panel costs in 6 months. You can buy 6 months of diesel, or you can buy a solar cell that gives you as much energy as that diesel in 6 months. And then if you bought the diesel, you need another 6 months, and then another 6 months, and then another 6 months, and you have to keep paying for it. But if you bought the solar panel, then it's free for 30 years. And if you kept investing that much in energy, why in just a few years you've got as much energy as the US, and then you got more. Right? This is a huge difference. There's a story, again, there's a couple of you who are old enough to remember this. We used to have to stand next to a wall to talk on a phone that was connected by a copper cable that had been required digging up chunks of Utah to get the copper, and Africa's not going to do that. They're going to do this. And they're going to look at this and say, 6 months of diesel, or I can get 30 years of solar. All right? There's no comparison here at this point. Right? So be very, very honest. It took us 100 years to build a decent fossil fuel system. Right now, there's something like 1 million gas pumps in America and 10,000 fast charging stations. There still is a real difference here. But if we burn the remaining fossil fuels before we switch, we are in deep doo-doo. We have scarcity. We are going to be fighting each other. It is going to be horrible. If we use those fossil fuels now to build a sustainable future, we get more energy more cheaply. Okay? We can recycle the renewables, and this can be sustainable. This will greatly reduce mining. Taking the mountaintops off to get at the coal is way, way, way more mining than is ever going to be needed to build all those solar cells and the wind turbines. There are some challenges. We keep wondering if we're going to be able to find enough rare earth elements and lithium, and then the material scientists say, we got you. We're going to be good. Okay? So, and then, rather than a world where everyone's trying to buy something really scarce from a few countries, everyone's got it. It's at home. You can make it your way, make it work for you the way you want to. All right? So, yes, this is going to take you students. You're going to be old before this is done. It's going to be your career, because we're going to try to do it faster than we did for fossil fuels to make it work. But at the end of it, you will have something that'll power everyone in the world forever, that'll give that whole world, including the poor people, what we have now, and it'll do it better and cheaper and faster.
It's interesting thinking back to the timeline that we've kind of put together here, right? So Arrhenius was figuring out that global warming, could be a thing, but maybe not going to be a problem. It was my dad's generation that said, oh yeah, this is a problem. We're going to demonstrate this. We have to do the science to show that this is something that we need to address. My generation had the privilege of advancing that science and of learning some of these solutions that were available to us. But in my generation, the argument went from no, global warming's not happening, to fine, it's happening, but there's nothing we can do about it. Students today are in the very first generation that we know there are solutions, right? We know this is possible. We know we have the technology available. We just have to come together and do something real with this while solving all sorts of other problems on Earth. That is the opportunity of today's generation. So, don't go for a long walk down a short pier. Don't fall into despair. We can turn this around. But seriously, we can. Thank you so much for being here and for everything you do to bring this forward.
So I hope we have time for questions. 3 minutes for questions. We'll hang around afterwards, don't worry. So yes, go, go, go.
So, how do you think fusion as a clean energy source, which is definitely in its infancy, how do you think that changes the calculus and how that's gonna change things?
Right, when I was a student, I was desperately excited by fusion. It was going to be it was the energy of the future. It was just around the corner. And it still is. And it's going to, right now they're talking about fusing tritium deuterium, and there's no source of tritium. We'd have to make that. We don't have a fuel cycle. There's going to be all kinds of issues on how do we permit that, because it will still be radioactive. You probably have to put it on nuke plant sites because you're already there. If you build, no one has a vague idea even which process will be running, and turning that into plants that are designed, optimized, running, market ready, and paid for. I can't see that happening until these students are well into their careers, if not old. Right now, we have seen in places that are unhappy, big energy installations like nuclear plants are military targets. People are trying to take over them. People are having all kinds of troubles dealing with them, where solar and wind are not. And so it's betting on, if it comes, if it's cheap, if it's easy, if it's fast, if it works, great, big smile, we're gonna all cheer. But counting on that for anything when you've already got the answer in your backyard, I think there's a lot of people pushing vaporware right now rather than the answers that are really here and that will undercut a fossil fuel economy right now. My opinion. This is also, I'm afraid, true of new nuclear, that nobody's built one in 10, gone from we want to build this to we're going to put it here to we have the money to we have built it to it's online. No one's done that in a decade. China can probably do it in a decade now, but whether we can. And right now, we didn't have it on the list, but if we'd have put nuclear on the list, what it costs right now, it's higher than anything else that was on that plot by a factor of 2.
All right, give him a round of applause for Dr. Richard.